day, everyone. Welcome to Waves, Optics, and Thermodynamics. I'm Sir Jero, and I will be guiding you through the exciting journey in physics. In this course, we will explore how wave moves, how light behaves, and how heat and energy interact in the physical world. Today's topic is all about Doppler effect, so get ready to discover the principles behind many everyday phenomena and deepen your understanding of physics. Okay, good day everyone. This time we will be discussing about the Doppler effect. Now, I have here an illustration, and I think that all of us experience this kind of phenomenon where when an ambulance is approaching, the pitch of the sound coming from the ambulance is high, and when it passes our position, you notice that the pitch of the sound from the ambulance is low. And this phenomenon is called a Doppler effect. Now, in the Doppler effect, we have two things that we have to consider here. The frequency of the sound when it is at the front of the moving source, and also the frequency of the sound at the back of the moving source, in this case, the ambulance. Now, take note that in our previous discussion, we talked about the wavelength, the uh, sound speed, and also the frequency. Those relationships are very important to establish the connection of the the frequency and with the length of the wave of the sound in the different position. Okay. Now, for computational purposes, we use different symbols. We use nu sub s. This refers to the velocity of the source. And for the listener, velocity of the listener, we use the nu sub l. And the speed of the sound, this refers to the how fast the sound is traveling in a particular medium. We use nu. Or sometimes we use the letter v, okay, to indicate. But in practice, especially in physics, we use the Greek letter nu to represent for the velocity. And also, the Doppler effect was first described by Christian Doppler, and he is a Austrian scientist during the 19th century. All right. Now this time, we have to discuss first the different equations describing the different parameters like the frequency, the wavelength, and the velocity of the sound when the source is stationary and the listener is moving. So in this case, consider listener as L, no? Moving with the velocity nu sub L toward a stationary source S. So the frequency that the source is emitting is represented by F sub S. And the same, the wavelength, the formula or the equation that we use to compute for the wavelength is still equal to the nu over F sub S, meaning that is the ratio of the speed of the sound, with the frequency emitted by the source. Now, the wave crest approach the moving listener at speed. So we are going to add the velocity, okay, the velocity of the sound traveling in the air plus the velocity of the moving listener. Okay. Now take note of that the nu that we used here in this formula. Okay. All right. Let me highlight this one. All right. This refers to the velocity of the sound in a particular medium. Now, in this case, in the previous example, we use the air as the medium where the sound is traveling. And the V sub L here, this refers to the velocity of the listener. Now, take note that the source of the sound is stationary while the observer or the listener is moving. It could be moving away from the source of the sound, or moving towards the source of the sound. So, the frequency heard by the listener is represented by this equation, and it could be computed and determined using this equation. That is, f sub L equals the sum of the speed of the sound in the medium, this one, plus the velocity of the listener. And the sum of these velocities will be divided by the wavelength of the sound. Okay. So, however, we understand already in our previous lesson that the wavelength can be computed by getting the ratio of the velocity of the sound with the frequency of the sound from the source. So let us first manipulate this equation to arrive with the final um, formula or equation, no, for the Doppler effect. So in this case, we're just going to substitute the V over F sub S to the lambda here. So the equation will be F sub L equals the sum of the two velocities, the velocity of the sound wave or the sound in the medium, plus the velocity of the listener. Now take note that we have to establish in our mind that in this case, the listener is moving. That is why we have the V sub L here. And over the V over F sub S. Now take note that the V over F sub S is actually the lambda. The lambda, as we know it, that refers to the wavelength, wavelength of the wave, which the unit is in meters or meters. All right. So, yes. So we just get the reciprocal of the F sub S here. That is why the equation becomes V plus V sub L over V times the F sub S. F sub S is the frequency from the source. Now take note that the V here, or the velocity of the sound here, is the denominator of all of the different of the two different velocities. So in this case, we could also rewrite this expression into V over V plus V sub L over V. All right, because they share the same denominator. So we could rewrite the V this expression that I highlighted here to this. Okay, so that becomes V over V, nu over nu plus V sub L over V. All right. Now take note that once the same quantities, or shall I say variables, are divided with by itself, okay, and that is equal to 1. That is why in the next line of the equation we have here 1, and retain the VL over V, so that is 1 plus V sub L over V, then multiplied by the frequency of the source. All right. So this is also the other equation that we could use to determine the frequency received. Okay, take note of that. The frequency that is being received by the listener. All right. So this is the equation that we're going to use. All right. So it is also important to establish the sign conventions, right? And also how the frequency behave, right? Now, if the velocity of the listener is greater than zero, okay, that means that it is moving towards the source. All right. So in this case, the v sub l, or the velocity of the listener, is positive. Okay, because it is approaching towards the source, or moving towards the source. All right. Now, if that's the case, okay, if that's the case, take note that the sound wave is traveling from the source to the different points of the surrounding in a circular manner. So, if the listener is moving towards the source, all right, it is somehow that the frequency is, I mean the wavelength, not the frequency. The wavelength is being shortened, okay? Because the listener is moving towards us, or at the same time, the sound wave is moving towards the listener. Okay? So what will happen is that there will be a higher frequency. That is the reason why when the ambulance is still approaching towards your location, you hear that the pitch of the sound from the ambulance is high. Okay? And when the the listener, okay, is moving away, all right, take note of that, is moving away from the source, all right, that means that um, the velocity of the listener is lesser than zero. Okay, so in this case we use negative velocity. All right, so what will happen to the frequency? The frequency becomes lower. All right, so the receiver, once the listener, take note of that, once the listener is moving away from the source, okay, moving away from the source, the frequency becomes low. All right, the frequency is low. Okay, so in that case, if we're going to relate that frequency, that low frequency, to the length of the wavelength, now the wavelength is now relatively longer compared to the wavelength of the sound when the source is still approaching. Okay, this is very important. So here, we establish that if you are moving towards the source, we're going to use the positive sign for the velocity. And if the listener is moving away from the source, okay, the velocity of the listener is negative. Okay, that is so important to establish because it will influence the manner as to how are we going to compute the 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 problem, or the or solve the problems that will be given later on. Okay. Okay, now this time the source and the listener are moving. All right, now suppose the source also moves with the velocity v sub s. Now take note that the v sub s here is again referring to the velocity of the source. Okay, this is not referring to the velocity of the sound in the medium. All right. Now, the wavelength in this case is no longer v over fs. Okay, and during one period, which is 1 over f sub s, the source moves a distance. All right, and that is denoted by this equation. Okay. So now take a look at this equation. We have here the velocity of the source. Okay, the velocity of the for example, in our previous example, the ambulance, the velocity of the ambulance is being paired with the uh, period. All right, and that is equal to Vs over F sub S. Okay, now if we're going to look at the units of this different quantities, we still arrive with the unit meter. Okay? Because m over s divided by 1 over s, we will get the reciprocal of 1 over s, so that becomes m over s times s over 1. Alright? So we could now cancel the second, and the remaining unit is meter. Alright? Now let's go back. Thus, the wavelength in front of the source becomes v over f sub s minus the v sub s over fs. Okay? Now take note that this v, or I mean the nu, right, over f sub s is referring to the velocity of the sound. Okay? In relation to the frequency of the source, of the frequency emitted by the source. So this is the speed of the sound in the air, okay, for example, that is 340 meter per second. And the frequency emitted by the source. And then the V sub S here again, the speed of the moving source, okay, or the speed of the ambulance, and divided by the frequency from the source. Right? So we're going to subtract both, no? The two different ratios, the ratio of the velocity of the sound and the ratio of the velocity of the vehicle or of the source, no, with respect to the frequency emitted by the source. So the final equation in this case is that v minus v sub s over fs. All right. So you have to establish in your mind that the v here is the speed of the sound. That is the 340 meter per second. In my reference, we use 340 meter per second. Okay, the speed of the sound in the air, right? And the velocity of the source, the v sub s. Okay.